All right, so this lecture is going to be all about recovering the correct units when using the Fourier transform and Morley-Wavelet convolution. And the issue here is when you do an analysis, so when you do an FFT or Wavelet convolution with, for example, EEG data, you know what the units are going into the analysis. They are microvolts, or maybe for MEG, it would be picoteslas or femtoteslas. And for fMRI, it would be bolds. Actually, I don't even know what the correct units are for bold fMRI, but whatever. So the different inputs can have different units. And the question is, how do you get out the same units? So if you're working with EEG, how do you get microvolt values back from your FFT and from your wavelet convolution analysis? This is a very tricky issue. And before I go into the details about how you do it, I would like to point out that actually you shouldn't do it. And I very strongly recommend designing your research so that you don't have to worry about the absolute units. The main reason is because these absolute units of brain measurements are not comparable across different methods. They are very obviously incomparable across EEGs, so microvolts and Teslas versus, this is still microvolts, but because the spatial scale is different, because the sizes of the electrodes and the impedances are different, you can't even compare EEG with LFP in terms of their absolute values versus light fluorescence for people doing optical imaging and so on. Even within a single one of these methods, even just within EEG, it's already extremely difficult to compare the absolute voltage values. For example, if you have the raw voltage data versus if you apply the Laplacian, now the units have changed from microvolts to microvolts per square centimeter. And if you change the montage, so comparing average reference versus earlobe reference versus CZ reference, the absolute values of the data will change. And I think this is meaningless. I think this is also an important issue. By meaningless, I mean that we shouldn't be interpreting the absolute values. We should be interpreting effect sizes or changes in values. I think this issue of making results comparable across different methods is becoming ever more important in neuroscience because neuroscience is gaining a lot of new techniques and a lot of new different kinds of imaging techniques and measurement tools and ways of using measurement tools. And increasingly, research labs are starting to do multiple domains. So for example, recording electrophysiology and calcium imaging. And so I think in neuroscience, it's becoming increasingly important to be able to link your findings, not just to your own tiny little pocket of the literature, but to other studies that use different kinds of methods, have different species, have different equipment, different montages, different processing streams, and so on, and leaving your data in the absolute measurement unit is just, it just makes comparing your findings across different studies extremely difficult and annoying. So there, I'm done with that tirade. I hope I've convinced you. So what's the solution? The solution is you should basically always compute and compare and interpret relative values. So you want to compare effect sizes or changes in activity relative to a pre-stimulus baseline or relative to a rest period or relative to a different condition. Somehow you always want to change your data to be relative values rather than absolute values. And I say almost because, I have to say that there's always the rare exception. There's always going to be the 1 out of 100 cases where it kind of makes a little bit more sense to keep the data in their original scale. So it does happen, but I think that's really very rare. I think the overwhelming majority of research findings in neuroscience can and should be interpreted in terms of relative values, not in terms of absolute values. I have a whole other section on of lectures about normalization and why you would choose other motivations for doing normalization. So I just listed one here basically, which is to be able to compare findings across species and methods. So if you'd like to know how to compute these relative values and normalizations, then you can look up these other lectures. But the point of this lecture is going to be how to get back to the original units. So now let's switch to MATLAB, and the rest of what we're going to do here is in MATLAB. So what we're going to do first is look at units from the FFT. So this is just, the static FFT, and we want to reconstruct the amplitude of the Fourier coefficients to be in the same units, the same scale as the original data. So we generate a fairly uninteresting signal. This is a sine wave at 14 hertz. It's a pure sine wave. It doesn't really do anything. It doesn't have any dynamics. But importantly, it has an amplitude, a signal amplitude that's other than 1. And whenever you are testing your code to make sure you can get back the correct units, you should never use an amplitude of 1. 1 is sometimes 1 is like a great number, but for these kinds of things, 1 is the worst number, because the square root of 1 is 1, and 1 squared is 1. So you could get the wrong answer, but you wouldn't know it. So use some value other than 1. All right. So here's what we have to do. There's 2 steps that you need to do in order to reconstruct, so we can pretend, these are like microvolts, whatever. So there's 2 steps. The first step is from the FFT, you need to divide the FFT by the number of points this should say by number of points in the signal. This seems straightforward. However, it is actually a little bit tricky, because if you do zero padding, then you still need to divide by the number of points in the original signal, not by the number of points in the zero padded signal. For example, so this signal is 10,000 points long, but let's say we wanted to double our frequency resolution. So we would go like this. The correct solution here is not, so you might initially think that what you should be dividing by is n points times 2. And this is actually incorrect. This will not give you the correct result. You always have to divide by the number of points in the original signal, even if you are zero padding. So I encourage you to try this with zero padding and see how it has to work. Okay, so that's step 1. Step 2 is you want to multiply the coefficients by 2, but this is a little bit tricky. So technically, you do not want to multiply all of the coefficients by 2. You only want to multiply the positive frequency coefficients by 2. And those are the coefficients that are between but not including the DC frequency, so the zero frequency, and the Nyquist frequency. So you have to find the components that go from, well, it's easy on the DC side because it's always going to be, the second coefficient, up to the Nyquist, but not including the Nyquist. And then those positive frequencies you multiply. So then you take the magnitude of the complex Fourier coefficients, and then you multiply those by 2. And that will give you the correct amplitude. So you see here, in the time domain, the signal has an amplitude of 2, and here in the frequency domain, the signal has an amplitude of 2. So doing any other manipulation here, you'll see that this will be incorrect. So this will not match this. And by the way, in case you're wondering why the amplitude is 2 when it seems like, I don't know, maybe you're thinking it should be 4 because it goes from -2 up to +2, then you have to go back and review some of the old lecturelets on extracting time frequency information out of complex Fourier coefficients. So that was for amplitude. So now let's do power. So actually, now that we know how to do extract the correct amplitude, getting the correct power is easy. You just add a third step, which is to square the amplitude. So, and now we can see this is also accurate. The amplitude is 2. Power is amplitude squared, so power should be 4, and here it is 4 units. So this, I have to say, most people, myself included, so people generally don't do this step, right? So most people would do, they don't multiply, well, let me make it even clearer. Most people would do this. They extract the length of the vector and then square the length of the vector. And then they plot that. And you can see that that's wrong. So power should not be 1 because the amplitude is 2 and the power should be amplitude squared. So technically this is the right thing to do. Now, again, at the risk of belaboring this point a bit, whether this really matters, I think, is difficult to. It's difficult to argue that this really, really matters, because if you don't multiply this by 2, or even if you multiply this by some excessively large number, of course that changes the absolute value here. So this is no longer correct with respect to the time domain signal, but this factor applies to all of the frequencies equally. So when you're comparing across all the different frequencies, the relative power doesn't change. And when you're comparing across different channels, different conditions, assuming this and different subjects, assuming this normalization factor is the same, the nature of the results won't be the same. Just the y-axis scaling will change. So just something to keep in mind. All right. Now we get to wavelet convolution, and now this is also going to explain why you need to multiply this by 2 at all, because I sort of showed empirically that it works when you multiply by 2, but I haven't explained why that is the case. So now let's get to the wavelet convolution. So here, what we're going to do is create a signal. This is a chirp. It's a linear chirp, so it increases in frequency. It starts at 25 hertz, and it's going to, over the course of 10 seconds, it's going to go up to 60 hertz. And this is just the formula for a linear chirp. And again, I'm fixing the amplitude to be a constant value of 2. Now we have our wavelet, and the wavelet's going to have a frequency of 40. It doesn't matter what the wavelet frequency is, as long as it's inside this range. You can try, making this 10, and you'll just get a flat line because there is no 10 hertz component in this signal. So anyway, 40 hertz, 20 cycles. That may seem like a large number of cycles for 40 hertz, but I want this to be a fairly narrow, fairly frequency specific, so it doesn't get too wide for the chirp. Needless to say, of course, I encourage you to play around with these parameters and try changing things. All right. So here we have the time domain signal. This is not all of it, it's just 3 seconds of it. Here we have the signal in the frequency domain. So this is a frequency domain version of the amplitude spectrum of this signal. So this looks different from the power spectra that you were used to looking at in neuroscience data. And that's because we have the negative frequencies over here to the left, and then DC is in the middle, and then the positive frequencies over to the right. This is, I typically, and most people in neuroscience typically do not represent our data this way, because it's typically not very informative or intuitive, I think. So typically you would, we just stop well below the Nyquist frequency. So we would typically, just show a range like this from 0 to 100. Or we have the negative frequencies all the way on the right. So you would see that this feature here would be all the way over here. I put it here because this explains why we need to multiply by 2 to accurately reconstruct the amplitudes. Typically, when you compute the inverse Fourier transform, so you compute the Fourier transform, and for a real valued signal, which, this is a real valued signal, our EEG data is a real valued signal. In fact, generally all neuroscience data is a real valued signal. when you take the FFT, the amplitudes get split between the positive frequencies and the negative frequencies. For a real value signal, those mirror each other. Now, when you compute the inverse Fourier transform, all of these get summed on top of each other. And the negative frequencies get kind of flipped over, they get mirrored over and summed on top of the positive frequencies. Now, when we extracted amplitude from the FFT here, notice we didn't flip the negative frequencies and sum them back on the positive frequencies. We actually ignored all of the negative frequencies. That's here, so we just take one up to the length of Hertz, which is going up to the Nyquist frequency. So what we did here was actually only take this side of the Fourier spectrum. We ignored all of this stuff. And because we ignored all of this stuff, we also lost half of the signal amplitude because this is half the signal amplitude. And that is why we had to multiply all of these positive Fourier coefficients by 2 in order to accurately reconstruct the amplitude. And the reason why we had to ignore the DC and the Nyquist frequency when multiplying only the positive frequencies by 2 is because DC and Nyquist are their own negative frequencies. So there is no negative Nyquist frequency, there's just one Nyquist frequency. And plus 0 is the same thing as minus 0, so we don't need to multiply that by 2 as well. So I hope that clears up this matter. And now, so this is the power spectrum, or the amplitude spectrum of the signal. And now here we have our wavelet. And remember, this is a complex wavelet. We need the complex wavelet. Where is this guy? We need the complex wavelet in order to be able to extract phase and amplitude information and not just get back the real part of this signal. Now, it turns out that so when you take the Fourier transform of a complex signal that contains a real part and an imaginary part, the negative frequencies are no longer simple mirror images of the positive frequencies. The negative frequencies contain different information, and the nature of that information depends on the sign of the imaginary component. So now the positive frequencies in the Fourier transform correspond to the cosines, and the negative frequencies correspond to the sines. And a complex Morley wavelet comprises cosine and sine components, so that's the complex part. And it just so happens to work out that the negative frequencies sort of, because the phase of the complex wavelet aligns just the right way with the negative frequencies of the Fourier transform, we don't get any non-zero Fourier coefficients in the negative frequency spectrum. Oof, stuff gets very difficult to talk about, but I hope you're following along. The point is that when you take the power spectrum of a complex Morley wavelet, there's nothing in the negative frequencies. All of the energy is contained in the positive frequencies. So therefore, we do not need to multiply by the amplitudes by 2 in order to accurately reconstruct them. And in fact, if you do multiply them by 2, as I'm doing here, you can see that you will get the wrong result. So this is not the correct amplitude for this wavelet. In fact, we know for sure that it's not the correct amplitude because I normalized it to have a maximum value of 1. But then I multiplied it by 2, like I did here, and here, and here. And now all of a sudden multiplying it by 2 gives us the wrong answer. And that is because in this case we do not need to multiply by 2 because we are not, well, you can think of, we're still folding the negative frequencies back onto the positive frequencies, but all the negative frequencies are 0. So I would also like to point out that this is technically wrong how I'm doing this here, because you can see I'm multiplying all of the Fourier coefficients by 2, when really I should only be multiplying the Fourier coefficients between, but not including 0 and Nyquist. So this stuff gets so annoying to do correctly that people often take shortcuts like this, which is, of course, in this case, it's fine. There is no DC component, or I should say the DC component is 0, the Nyquist component is 0. So 2 times 0 is still 0. So here it doesn't matter. I just wanted to point out that, yeah, even in this lecture where I'm supposed to be telling you how to do it right, I'm still doing it wrong when I don't need to be doing it right. So finally, now we get back to the reconstructing the correct amplitude and power with wavelets. And basically, so that part works fairly similarly as getting the amplitudes and power from the Fourier transform. So again, technically, we should be when you're extracting power, multiplying by 2 and then squaring it. But most people don't multiply this by 2. Most people would just take ABS and then square it. And then, oops, I have to run this part again. And you can see that's technically not correct. But again, you know, I'll set that back to 2. So let's see. So this is the correct way to do it. But again, I would like to close this lecture by begging you not to lose sleep over this issue. If you really somehow need to have the units to be back, or the results of the FFT and wavelet convolution to be back in the original units of the data, then it's fine. You can follow this code. But I strongly encourage you not to worry about this kind of stuff at all, and instead to use a baseline normalization that allows you to interpret your results more safely, and also allows you to compare your results across different imaging methodologies. All right, I hope I haven't confused you too much.